All right, looking for that green light. It's coming, I know, I can feel it. There it is. And that means I can do this, and I can do this, and there we go. All right, so class is here. You can see my iPad. Here's the website. Once again, a couple notes, news and notes. Again, we will not have homework. Homework 2 is now due October 3rd. So hooray, hooray! That's good. This is kind of cool. Okay, I want to walk around with an iPad. See how this goes. Can you see it? Okay. All right. This is different. All right. So, but also on that note, this is iOS 11, which is kind of cool. We left off last time on model fit. Uh-oh. No, this happened with PowerPoint before too. The problem with all the Apple stuff is when you start getting with Microsoft. You can see my passcode. My passcode. Series of numbers, if you'd like to know it. It's my phone number. So yeah, I love that.
Is it the same for our grades?
Absolutely. Absolutely it is. You know it. All right, let's see how this works. So, what do you remember from last time? Model fit indices, that's right.
Can we say Jonathan is prone to fits?
Oh, yeah.
Can we say that?
Oh, that is good. Touche. If I could give extra credit out for jokes or puns,
I would get an A.
you'd be on top of everything, Jesse. So yeah.
Good to know that.
Actually, you know what we should do? We should make it sort of like a one-upsmanship, or like try, if anybody can beat that, whomever gets the best pun of the day gets an extra point. No, I can't do that. That's probably not good.
Well, there goes me paying attention.
Trying to get a pun in. No, it's okay. Everybody gets points. We all get medals. We're good. Model fit. What do you remember about model? There's lots of fit indices.
We have 5.
5? There's like 50 million. But why is fit important? I think that's probably the big picture.
So you can judge the normal and model.
Because if it doesn't fit, what happens?
All the assumptions you make from your model are biased.
Everything's biased. It could be biased. Could be biased. You can't definitely know. Yeah. So no model fit. Could be biased. Could be bad. So last time we saw there were some steps in model fit. We had this global fit. I like the chi-square test.
Sorry, I was just.
No problem. Just making sure. I'm just waiting for something to go wrong with technology. So, but so far so good. This is pretty amazing. The chi-square here, the first place I look is the likelihood ratio test, right? And if we wanted to see exactly where that was, I go to Safari. I'll pull up the example. And I'll do the simulated one. And this is where I finally am excited, because I used to have a Surface. Actually, Surface is what got me off of Microsoft. But I found I could do drawing on my web pages with it, right? So I think I can draw here too. So I can highlight things. So this is our example file. If I go down, pardon me for scrolling so much. Get down to model fit. Uh-oh. We have a problem. Page too long. Okay. I won't actually scroll. Okay. Delete PDF. Let's just go down here. I won't draw on it. I'll just highlight it. So in model fit, teach me for doing such a long example, right? In model fit evaluation, the part I like best when we look at this is this one right here. Oops. Right there, this one. That model, that minimum function test. I like that one. That's because I have a statistics fit. Right? That was my heat map, right? If you get this to be non-significant, everything else works well. That's good. But remember, that was sort of my favorite. After that, we started to go into RMSEA, which needed to be, it's a root, so we want it low, like on the ground, and it needs to be like 0.05. And we see here, 0.215, that's not good. Is this effective at trying to get what I'm pointing at across? Okay. Let's see if this works. So after RMSEA, then I said CFI and TLI, which are in the middle here. And these ones we want to be high, they're an index high. Want them to be close to 1, 0.95 or better is what we like usually. And then finally after that, the standardized root mean squared residual, or SMRMR down here, that one, we want that to be less than 0.08. But if you look at this index, look, it's less than 0.08. I don't know where that comes from. Not good. So, those are the, does that jive with what you remember? Sweet. At least I'm being consistent. There's a little reliability evidence for you. So what happens now? You got model fit. What do we do when we saw there was no good, model fit wasn't good? What the next step is. We saw last time, I just put it up, the RMSEA was like 0.21. The overall global model fit, the chi-square test of model fit wasn't good either. I'm gonna sit down. You guys mind if I do that? Try to do this. So instead we want to look at localized model fit. Right? So what I mean by localized model fit, this is where I can go to notes, perhaps. And we're going to start drawing. Do you remember? Yes. Okay, so do you remember in the CFA model, what we end up coming up with is a covariance matrix, right? So we end up getting our, what we sometimes call predicted covariance matrix. Right, and the CFA model that comes from the matrix product, I'm gonna call this sigma hat, right? So it's like our model estimated version of it. Technically speaking, our sample estimate is 2. So actually, one thing I should probably differentiate this by is saying, we're gonna call this sigma. Sigma comes from the model, right? As opposed to S, which comes from the data, which is our data covariance matrix, right? So in sigma in the model, it was this crazy matrix product that if we put all the factor loadings in a matrix, lambda, we put all the factor covariances in the matrix phi, we took lambda transpose, plus the matrix psi, which is our matrix, matrix of residual variances and covariances. That gives us what the model's version of the covariance matrix happens to be. But we also know the data's covariance matrix. And actually this is right here. This is the H1 model, the saturated model. Right? So there. Right? So this comes from this is what we would call H0, right? The null model. Right? So if we saw we've seen in our slides, and we've seen over and over again, that in these typical measurement models, the only places where model misfit is going to occur is going to come from the covariances themselves, because we're going to get the diagonal of this thing. We're going to get so it's, if we look at this looks like, with 6 items, it's this 6 by 6 block, right? And down the diagonal, these are variances, right? And in the off diagonal, we have covariances. So, right over here. Right, so the variances are going to be right. It's these ones right over here that are going to be all off. And that's what we have to go and try to figure out. We have to figure out how we're going, if we look at there, we can get a good glimpse as to where the model is not fitting the data as well as we would like it to try to modify the model itself, right? And so one way that we can look, if you think about it, what we can do is we can take the difference. If we take, don't need that. If we take S, if we take sigma minus S, what do we get, right? The places where our covariances are too big, this is a residual matrix. This is not root mean squared residual. This is related to it, but is not a root mean squared residual. There's too many words residual so far. This is a residual covariance matrix, sometimes called the discrepancy matrix. And I don't know how to spell discrepancy. Is it an E-A-N-C-Y or is it? Okay, good. So you'll see my problems with English show up, right? So what you'll see here is this: if our model matrix is too big, what happens, right? If the covariance in the model is too big, this should be positive, right? So we overestimate the covariance. If it's too little, the off diagonal will be negative, right? So we underestimate. And sure enough, there are things to do whenever we are in such a situation, right? So what we want to do is come up with a residual matrix, right? Which is effectively what the model says minus what the data says, right? H0 minus H1. But we're going to come up with a type of one that's sort of invariant to scale, right? So covariances themselves are on different metrics because the variables that contribute there have different variances, right? So if you have one variable with a huge variance and another one with a small variance, that covariance is going to look very different than of two values that are variances of one. And look, if you want to talk about this, look no further than the correlation coefficient. Correlation is a covariance between standardized variables, right? And we know what scale they're on between -1 and 1. If our variables weren't standardized, you don't know what scale they're on. Right? So that's why we want to come up with something called a normalized residual covariance matrix. Yeah, Jesse.
A second ago, the equation that you showed us for the discrepancy matrix was sigma minus s.
Mm-hmm.
But then you said we were going to use the HO minus H1. So we were going to subtract our predicted covariance matrix
That's right.
from our original covariance matrix.
That's right. So right here, HO is sigma.
Right.
H1 is S.
Okay. So sigma minus s.
Yes. Sigma minus S.
And on the flip side.
Predicted minus actual. And the reason for that is we want to see if we overestimate or underestimate. Right. So if we put predicted first, then the overestimates will be positive. We can flip the order around.
And do everything.
Yeah, we'd still get the same information, but what our standard of reference is our model over or under fitting the covariances. Got it.
I think this depends on the sign of the in front of
That's exactly right. That's all we're talking about is a sign. But we're going to make conclusions about it regardless. If it's non-zero, it's a problem. Jada, did you have a question?
Yeah, so if your sigma is greater than S,
Mhm.
then that means you have a positive residual.
That's right.
And then does that mean that there's some sort of interaction or something that's happening?
No. Positive residual. It's just there's more than just the factor that's creating a covariance, right?
So what could be the things that are?
It could be some other factor on the item. It could be some type of design effect. So what happens basically is it's saying that what you're basically saying is that there's something else out there that's giving this pair of items more covariance than just the factor itself, or the model is saying. I mean, if you have one factor, it's easier to see. If you have two, it becomes sort of an issue. What could that be? Right? Well, it could be this other factor out there that is causing extra covariance, right? So maybe you think there's one trait, but there's really two. It could be something like a design effect, right? So it could be that this is a negatively worded item, and there's something about the negatively wording that's causing issues, which almost always happen by data. So it's just something else additional that's the problem for it. Does that help?
Yeah.
Okay. By the way, if this goes blank, can you let me know? I realize one flaw in the plan here. So you're like, wait, just interrupt me. Get mad, throw some paper, something like that. That'd be fun. So what do we do? The other way that we can actually work on this is something called a modification index. Modification indices. Some people call those voodoo. All right. So this is kind of one of those interesting things in statistics. There are in maximum likelihood-based statistics, there's these 3 tests that are out there. We've seen 2 of them so far. We've seen the likelihood ratio test. Right? Likelihood ratio test. Here. You don't want to see my calendar. Yeah, you don't want to. You're going to see all my details over here. Make sure they're sanitary. Actually, most of them should be sanitary. My passwords may not be. There are 3 tests in ML, right? In ML, maximum likelihood enabled test, I would call it, right? No, full information is all what we're talking about here for maximum likelihood. So for the most part, there's some equivalence cases, but full information, we're using all the data, and that's what we're going to almost always assume. The first one is the likelihood ratio test. Oh my goodness. Right, and you've seen that. To do this, we have to estimate an H0, a null model, and an H1. We have to estimate two models, right? Right, and we compare the negative 2 times the log likelihood, sometimes rescale it, we get a result. Another test is a Wald test. Right? What is a Wald test? That's the z-value that goes with every parameter. Right? So if you want to tell whether or not a parameter is significant, you keep looking in the parameter output. Here we go. We can actually see all of these tests in one bit of output right here. The output up here is the likelihood ratio test. Right? That is the likelihood ratio test right there. That is telling you that Levon fit the saturated model, H1, and it fit the null model. Took negative 2 times the difference in chi-square, rescaled it by the robust maximum likelihood effect coefficient, and gave you that. So if you wanted to test whether or not one of the loadings was significantly different than 0, you could use a likelihood ratio test because you could fit a model where the loading was present and estimated. Fit the same model where that loading was fixed to 0. We do a likelihood ratio test with their negative 2 times the difference in log likelihood to have 1 degree of freedom, and you get your test, right? The Wald test, that is like looking right here. If you wanted to tell whether the factor loading for SIT2 was different than 0, here's your test statistic. It's a z-value, but you take the parameter estimate divided by the standard error. Under ML, as n goes to infinity, this thing becomes normally distributed, so we use that to our benefit. We look at the p-value and we say, lo and behold, yes, it's significantly different from 0. Right? So in the Wald test, basically we just have to fit H1. Right? We fit the model with the parameter in it, and we look at the p-value. So there's one other test you could envision, right? This is kind of the magic of it. This is something called the score test. Right? So up here we fit both. Here we fit H1. Imagine what the score test is. We just fit H0. What does that mean? That means we estimate a model without the parameter we're interested in. Right? It's not in the model. It's not there. But we're going to create a test statistic for it and a p-value for it to see what it would have been if it were in the model itself. And this is why it's voodoo. Right? Where does that come from, right? It wasn't even there in the first place. Well, there's this beautiful likelihood theory. Rao was the person who kind of did the score test back in the 1940s, so it's been around forever. But basically, it's like if you didn't put this statistic in your model, can you come up with some information? Can you use that to, can you use features of the likelihood function itself to come up with what that might have been had you put it in? And in SEM, that's what's called a modification index. So that's why we call them voodoo. Right? So we're going to see that we get two types of information out of the system. One is based on the residual discrepancy matrix, how close our model is fitting the covariance. The other is based on this set of statistics that are based on likelihood theory. That'll say, hey, there's a whole bunch of parameters you didn't put in the model. Right? For us, it's hard to tell what they are, but both of those pieces of information used together can help you figure out where to put things in the model to make it work. So let's take a look at these. Let's go back to our example. Is this working or is this getting too confusing? Am I getting too much? So we keep going down here. There we go. And the first thing we're going to take a look at got modification indices right here, right? So we saw that the global model fit was no good for this analysis. And so what we can end up doing is tell Levon or tell our system to get modification indices, these voodoo tests, score tests for each thing. Another synonyms that get used in statistics, we call this a score test or a Lagrangian multiplier test. In SCM, it's called modification indices, and that's because we're in the world of bubbles and circle plus triangle equals square or something like that. Right? So we tell it this function right here, modification indices, and in parentheses we give it the model object that Levon estimated. Right? So this is model 1 estimates. That's what we used the SCM function above for. Right? We told it right here. Well, it's way up in the text, but model 1 estimates is there. And we can actually have it sort the result by the highest to lowest value. So let's take a look at what each of these values happens to be. Let's see if I can.
So, like, I see correctly, it's sort and something comma.
Right, so we tell it sort
Sort
dot
dot.
equals true. Yeah. So what that means is order the index from the parameter with the largest value. Right? The largest value means this thing is glaringly needed in the model. Okay, so here's where I'm going to try iOS to my advantage. I bring this and there we go. Go side by side. This is not good. You can't see this table. Let's see if I can. This is where anyone download iOS 11? No. I want to make this into one. There it goes. That's what I wanted. Okay. There we go. Of course, it's here. Sorry.
Can we do this on the Mac or on the iPad?
The side by side. You can do this on the Mac if you hit the green arrow to maximize and hold it. It will actually do that side by side. So here we go. There it is. All right. So I'm going to write over in this side over here what each of these are. What we see on the first is LHS, OP, and RHS. What that's shorthand for is what's happening in the Levon syntax. Right? So this is the left-hand side. OP is operation. Right? That's the Levon syntax for what you want to do with that parameter. And RHS is right-hand side. And so operations, if we look here, sit2 double tilde sit4. If we were writing that syntax, that would mean what in Levon? The covariance between item 2 and item 4. And what this is telling us is sit2 versus sit4. The MI, what we want to look at here, MI, the next column, this is the chi-square value that would happen. It's the estimated chi-square if you fit the model with that parameter in it and did a likelihood ratio test.
Is it the estimated chi-square or is it the estimated reduction in chi-square?
It would be the estimated -2 times the difference in the chi-square statistic. So like if you fit, right, so MI, if you fit a likelihood ratio test, right? So you have H0, which is your model, without parameter, right? And you have H1, which is now with that parameter. This chi-square comes from -2 times the difference in log likelihoods. Right? So I guess you'd call it the reduction in likelihood. Well, I guess it's reduction in -2 times.
Right.
Sorry, the logic of it's there, but that's where it's coming from, right? So if you were to, where you could come up with this is if you were to go and add that covariance to the model, the residual covariance, but if you were to add it to it, that 2.02 or 20264 that's right over here, that right there should be the value of the likelihood ratio test if you compare the two models. This is a chi-square, and it's a chi-square with a 1 degree of freedom. They're all 1 degree of freedom tests because one more parameter would be added to the model, right? So gotta remember that. You like say, oh, what's this? So what is what is the significant chi-square value with 1 degree of freedom? 3.84. Right. You sort of get used to this number, right? So if this is greater than 3.84, it says that that parameter would be significant if added to the model, right? So what does that mean? What is the next column? MI scaled is really what we should be looking. This is MI scaled is for the robust maximum likelihood estimate. That's like the right-hand column in the bottom. Right? Shade it.
So you said that if any of those in the MI column are greater than 3.84.
That's a parameter we could add to improve the fit.
Right. So then you would add all of those parameters?
No, actually.
Because
First of all, what you're going to get from the computer may not be even possible to be added. Sometimes it'll give you a parameter that shouldn't be there in the first place. But that's not the case here. Because each of these is a 1 degree of freedom test, what this is telling you is if you were to add one of them from this whole set, that's how much the fit would improve. Right? So the temptation is to be like, I've got 25 items, so look at all these numbers that are bad. What typically happens is when you add one, then the fit gets better. You redo this, and all of a sudden you start to see things get a lot better. How do you pick which one? Good question. I'll get to you just a second later. The best idea is one that's guided by. What I like to do is look at the overall results here first, and try to make sense of them, and based on that, try to make a modification of the model. Right? It may not be the case that what we're getting here is that one factor doesn't fit these 6 items well. So let's see if we can take a look at the pattern of modification indices and the pattern of the normalized residuals to make sense of where the model is off, because we might not just add a parameter, we might add an entire factor, right? Because you see right here, each of these operations under this column here, this operations column, they're all the double tilde, which means they're all residual covariance. It's not telling us what would happen if we added a brand new factor, right? So when your model doesn't fit well, there's several options, right? Just, Katie, to get to your question, several different paths to take, right? Paths. Sorry for my handwriting. One is add single parameters. That is basically saying I'm trying to put band-aids on a problem, usually. 2, add factors. Adding factors, less of a band-aid, kind of more of a structural change. It needs to have good rationale for it. Actually, it needs to have good rationale for single parameters, because people will say if you add a residual covariance, yeah, but if you really believe there's one factor there, there should be no covariance. Why did you add that residual? Oh, there's another factor involved. I just don't know what it is what the answer usually is, and that becomes a problem. If you don't like that one, usually adding factors is a little bit better if we can justify it. You know, I thought there was one situational forgiveness factor, but really there's 2. The third option, this is the option that you see almost always in educational measurement, is to drop items. Okay? Because in dropping items, it's easier, but there's sort of a measurement of latent variables. Because they don't exist, we sort of create our own reality. Right? So each one of these paths is sort of problematic in its own way, right?
That's why we shouldn't have a lot of items in case you want to drop some.
Dropping items, the rationale for it is, yes, have a lot of items, drop some. Another rationale given is sometimes the item just didn't get interpreted by the people in the sample the way that you built it originally, right? So the model misfit is inseparable from poorly written items, right? You write a bad item, it's probably not going to fit a model. You write a good item that doesn't fit the model, they're both the same. You can't tell, indistinguishable, right? So one argument people use, particularly the people in this cult group called the Roche modelers, I said that internet, the Roche models are a cult group. No, I'm just kidding. We'll get to the cult group in a couple of weeks. I'm serious. If you look up Roche.org, there's like pentagram. But basically, they believe that if the data do not fit the model at all, the problem is not with the model, the problem is with the data, right? And so therefore, regardless of why the item is out. But what this effectively does is really makes measurement difficult because you're sort of homogenizing the items to fit this model when really ecologically it may not do that.
That's why the researchers or whoever develop assessments, they do focus group and then like small sample size first.
Yeah, a lot of pilot testing.
Yeah.
Mm-hmm. That's what the goal is, but most people, I would say a lot of the research that gets published is not done with that. So let me get to Michael and I'll get to you, Shada. Michael.
I think you kind of answered. I
Oh,
was
is
going
it?
to ask if you would just drop item 2 given the number of
Yeah.
significant covariance.
How would you know which one to drop? I would look at which item shows up the most. Item 2, item 2, item 2, right? Go down the list. Shada.
So what if you have a case that you have your model and you find that you have one item that equally loads on 2 factors, and you just decide based on your theoretical framework that it fits better in like this factor subscale.
But that makes your model fit that.
Well, yeah.
Well, usually it's the case if an item equally loads on 2 factors. Are you saying you estimated the model with 2-factor loadings for that item?
Yes.
Okay. So, see, my philosophy is okay. Then the data are telling you something different than what philosophically it's at. So where do you resolve that? If you remove one of the factor loadings, the model still fits well enough, then you can sort of argue it's inconclusive about the data. But if you remove one of the factor loadings, the model doesn't fit well, that's where you get that problem because now the theory is that the data are saying that it doesn't match with the theory, and so then you've got to figure out what to do with the theory.
So then would the easy fix in that situation be drop that item?
It could. I see a question.
It's not that question, it's a kind of a comment. Because I'm trying to make sense of what you are talking about here. I feel like there should be a threshold in this process because
Oh yeah, for what's the biggest value?
not the biggest value that we add single parameter or we add factors because now we are exploring.
Oh yeah, this is exactly what we're doing. We have switched away from confirmatory analysis and we're now doing a very targeted exploration with areas where the model is not fitting well. That's exactly what we're doing. And this is where I say, if you're going to do EFA, don't use EFA, the methods that are broken for a lot of reasons. Use this type of method, right? We're no longer confirming, but we're not exploring in the dark, right?
So what we should like if we would report it in a technical way, should we call it confirmatory or confirmatory?
You would basically say exploration through confirmatory factor analysis, right? You have to say something along those lines, and you want to give the story. You want someone who takes your data and your scripts to understand why you made the decisions that you made. But along those lines, another reason why this is called voodoo is that each one of these, each time that you use one of these, it's a hypothesis test. And we said to be a significant value, you have to pick an alphabet level where significance happens. And we said 3.84 is the minimum level for 0.05 significance for the chi-square. That's for one test. If you repeat this process 15 times, you're likely to add parameters because of type 1 errors. Right? It's no longer an overall 0.05. Remember the Bonferroni correction you had to make before where you had, that's effectively where this also happens. Sometimes people call it p-hacking, where you're sort of looking for the most minimum statistic and doing it. So one way to guard against that is to use a very small p-value for this test. Only indices that are really large work. M plus, as a default, uses the value of 10. Right? Any chi-square that's over 10 effectively has a p-value that's out to the fourth, 0.0001. I can't exactly. I don't have the ability to type it in on here to find out exactly what it is, but it's small. And that if you have a chi-square bigger than 10, you should feel comfortable in adding the test statistic because even if you add that 100 times, you're still not your overall type 1 error rate for what you're doing is likely to be small.
If I understood like what you are saying, and also what I have read in the book, like in Brown, value we have for the parameter is positive, it needs to be added to the model. If it's negative, it needs to be removed.
It can be. Yes. I mean, sort of. The problem is, it's not that just. So people talk about each of these as being separate from each other. The reality of it is they're all yoked. They're all tied together. And so when you see something that's negative, you often see something that's positive as well. And so you address the positive, and all of a sudden the negative gets better. So it's something that it's more of a field. Generally, let me get through this, and we can talk about more of the strategies right now. So let me just get through modification indices, what they are, what each of these columns mean. And then we're going to get to the residual covariance matrix, because I want to give a snapshot of what happens. And with this example, there's a pretty clear, what I think is a pretty clear evidence for what's happening, to give you something to anchor to. Because right now I feel like we're like, oh, but what if, hold on for just a second. Let's go through the rest of the columns. Okay, so this is the chi-square column right here that you want to look at, MI scaled. What does EPC stand for? Very good. Expected parameter change. What does that mean? Well, this parameter in your model, bless you, was set to 0. So it should go up by 0.648. Yes, it's a change. But that means if you were to estimate the model, you would expect this value of the parameter to be close to 0.648. It's not going to be exact unless you have a super infinite sample, but it's going to be close to that. Then each of these other columns is that same value, but based on the standardization that you like, right? So this is the standardization where you fit the standardized latent variable. That's like the column that says std.lv in the output, right? That's saying, had you identified the model with a factor variance of 1 and a factor mean of 0, this is what the value of the parameter would be. So they match up because this is how we identified this model here. The next one is if you had standardized the model where if you had standardized with respect to the item itself. So this is if you had standardized items, but you also had standardized factor. This is what it would be. And this last one only really matters when you have categorical indicators in the model, categorical variables, so we don't really talk about it. We'll talk about it when we get to that spot in the analysis. Right? So that's what each of those stand for. How we doing? Okay. So here is the residualized covariance matrix. Right? So what we're going to do, and actually I have been backwards on this. Observed minus predicted is really what we want. S minus sigma. I always screw that up. Sorry. But you can tell it's really important, right?
So sigma minus.
I had sigma minus S here. Really, this is S minus sigma.
The latent C is the difference?
Yeah, the difference between the model. So I'm going to make this big. What we're going to do here, if you want to see the residualized covariances, the function resid is used. Again, you give it the model object in Lavon that you estimated, a model 01 estimates. And there are different types that it will give you. This is the raw, this is the direct subtraction between what the model version of and what data say. So again, this is sensitive to scale, and it's hard to tell which one of these is really informative. If we go a little bit further, we said type equals normalized. Right there, that is the one I like the best because the values that you see in the normalized are like z-scores. So what you would look for here is a value that's big, a number that's bigger in absolute value than 2, effectively. I mean, you really want to be sure like 3 or 4. So let's take a look at this story that we see here, right? Okay. Situation 4 with situation 2. That says a very large positive covariance between those two. Situation 4 with situation 6. Very large positive correlation between covariance between those two. Situation 2 with situation 6. Very large positive covariance between those two. So all of a sudden, sit 2, sit 4, sit 6 share something alike in that you notice how I've named these. Sit 1, sit 3, and sit 5 are reverse coded. Sit 2, sit 4, sit 6 are not. And This is like the first place I look at when I've got a CFA. That reverse coded items usually almost always screw up the analysis because the reverse coding is not the same mentally as we do mathematically by taking the reverse side. Sure question.
How do you know that it's because it is that it's reverse code?
How do I know it's reverse
Yes.
coded? Because that was what came in to me as the statistician.
No,
So somebody wrote the scale and wrote the items so that it'd be
so
negatively
you
worded.
look at the item itself.
That's right. You look at the that's right. That's right. A lot of times when you see scales, people will have like if you see published articles for it, you'll have all the questions and you'll have like an R behind it that says reverse code this, something along those lines.
Why do they reverse code it?
Sometimes they do it because they want to. I've heard a rationale being that you want to see if the person's paying attention,
Oh, okay, now I know what you mean.
right? Which is really I don't like that rationale. Have anyone used MTurk, the mechanical Turk through Amazon?
It throws the participants away.
It does, but you can create better items than that for people paying attention online. Like the answer to this item is 4, right? Or if you're paying attention, click the third option, right? Because you'll be able to do things that are attention checks that aren't part of your factor at all, right? So you're trying to do that. There's other methodological ways that we can handle that. There may be other motivations for it as well. I don't know what those motivations are. I'm not good with this is like a survey research question. Does anyone else have any motivation for reverse coding you've heard of?
I know one reason is when he reverse coded item, writing the item is more easy to understand because some latent factor you have to reverse writing that to make people understand.
Right, there may be some catch with the factor that makes it easier to like positivity versus negativity, or right there's the planets, right? Positive affect, negative affect, right? And so you'd see they're not necessarily polar opposites of each other; they're their own feature themselves, right? So while it may look reverse coded, they're actually the reverse coded items for like the negative affect, they're actually positively coded for negative, which is but
Would
there are.
that even be technically like reverse coding though, or would that just be like satisfaction and frustration, or?
It sort of blurs the line, right? And so technically, if all the items were in the same direction and they were all negative, then it's not reverse coded.
Right.
The literal what I'm on this mechanism, the literal version of reverse coding is where you took a look at someone's scale and when they did strongly agree, instead of giving it a 5, you gave it a 1 or something like that, right? So the actual mathematical translation for it. But no, you're right about that. There are certain natures of certain traits that cause that to be a problem. And then you come up with what's reverse coded for a negative scale, right? So like the logic of it becomes a mess, but there are ways. I mean, it's hard to describe in abstract, but when you're writing your own scale or when you're in your own field, you'll be able to see it a lot better. If that helps. Okay, so let's see here. Let's try out this hypothesis, right? You saw that sit2, sit4, and sit6 had positive covariances with each other. Sit2 and sit1 is a negative value. Sit2 and sit3 is a negative value. Sit2 and sit5 is a negative value, right? So you're starting to see this pattern of positive and negatives show up in the data, right? Or better yet, sit3 and sit1 are positive right here. Sit5 and sit1 is positive. Sit5 and sit3 are positive, right? And 4-2, yes, 4-2. So do you see what I'm saying? Like you're seeing this whenever you have items that are the same coding style, right? Whenever things are not reverse coded, they have an overall, or whenever an item that's not reverse coded is matched up with another item that's not reverse coded, you end up getting a positive covariance. Whenever there's an item that's reverse coded matched up with a reverse coded item, you get another positive covariance. But when you get a reverse coded item paired up with a non-reverse coded item, you see a negative covariance. So there's this pattern, is what I'm trying to get at. And so this is another way to do this. And so in this case, this is where Lisa had built this analysis. I don't disagree with her. That this is something that says, what if there are 2 factors? What if there was a positivity, like situational forgiveness positive and a situational forgiveness negative? Now, not being a situational forgiveness researcher, I don't know what that would do, but let's imagine that this is the case, right? So what would we do? Let's build a two-factor model. So to do a two-factor model, it's very similar to a one-factor model. We're going to come up with a factor named SIT-P. That's positivity. And we're going to put on that the coded items that were all in the positive direction. We're going to come up with SIT-N, which is negativity. We're going to put the reverse coded items on. Now I'll note, this two-factor model, I almost went to draw on the board, and I don't have to do that. That's one of the things I did this for, is because if you're watching, away from here, I can actually draw, and you can see what I'm drawing. I feel like I sound like I'm talking to my son. You can see what I'm drawing, Hugh. All right. So with the two-factor, right, we've got, this is y2, y4, and y6. And we've got positivity here. Hooray, positivity. And over here we've got negativity. Bummer. 1 y, 1 r, y, 3 r, y, 5 r. And what's going to be estimated automatically is a covariance between these factors. What I'll also note is there could be an alternative way that you might want to work with this, and that's actually something that shows up a lot more often in research, where you have negatively coded items, is that something called a method factor. We'll cover this a little bit more in a couple weeks. But let's imagine you had something called situational forgiveness, as we called it before, and again, we'll have this get measured by each of the items, but now you've got this like reverse coded factor, and all it does is it shows up on these three, right? And if you do that, now you've effectively got your one factor you're interested in, and you've sort of controlled for the influence of the reverse coding, right? So each of these items over here, each of the three items on the negative side over here, are going to have two factor loadings. Right, but that factor loading for that negativity factor is effectively providing the rationale for saying, okay, these things are extra correlation, or maybe not. Actually, we're trying to remove that correlation. It shows up. So you'll note once again, though, we talk about Brown's book, where a negative covariance, we got to take something away, and the positive covariance, you got to add it. It starts to get dicey. What you're going to see is this model is going to fit a lot better, and the negatives are going to be less negative, and the positive ones are going to be less positive, and it's going to be, so like the solution is not as simple as like add stuff here and take stuff away there. It's more trying to see if there's a holistic way. If you're wondering where you go with your data, I'd say look at the normalized residuals, try to make sense of them if you can, right? Look at the modification indices, try to make sense of those if you can. And again, if we look up at the modification indices, knowing what we just saw, you'll look, the biggest modification indices are always items that match the same positivity or negativity, right? So there's sort of a pattern we saw there. In the absence of either of those, if there's not an obvious pattern, that's where you start to think about adding those one parameters that might tweak the story just a little bit, if it makes sense, or removing items that show up in a lot of these places.
Right. So say you do this, and you do establish that you do have like a positive factor and a negative factor. Then you said to look at the covariance between the two, and you would expect it to be.
Well, let's find out. Okay, so let's see. Here's model 4. From the model fit, take a look at the likelihood ratio test. That's a test Templin would like. The p-value is good, right? So what you would expect here is you'd like to see that all the modification, or all the fit indices are good, and sure enough, 1 for the CFI, 1.004, even better than 1 for TLI. That's where we start to squirm. RMSCA of 0, like that's spot on, right? SMRMR of 0.006. Now, again, all this could be, you could get this rosy information and have no correlation between the items, but you'll see this test, this one right here, the minimum, the model test baseline model, remember that was the test comparing the saturated model to the independence model, right? The one with 0 covariance. that test is identical for any model that you run because it's always saturated versus independent. So this tells us there's some covariances to be had. So now we can look at our results, and here's what we find. So we'd say this model fit, right? Even Templin would agree. And Templin's like a model, like a really strict, like I don't know what you'd call me, like a throwback model fit person, or like joking around, we used to say things like model fit Nazi, but in the modern light of where that word gets used, I don't want to use that, right? That is not a good one. So I would say, even with being, I insist on ridiculous fit. That's being ridiculous fit. That's a good thing. So it fits. We can interpret the results. The correlation of covariance between the factors is 0.611, but we standardize those factors. That's covariance, the correlation, which by the way you'd find right here. 0.611 tells us there's two unique factors. Here's the situation that we get into very frequently in CFA though. Yes, they're correlated. They're going to be. Almost everything that you measure from a person is going to be correlated with something else, right?
So you said this 0.611 on the standardized all is a correlation.
Yeah, standardized all is going to be the correlation between the factors. Actually, standardized LV, what you should see is both of those will match up with the factors. So depending on how you've identified it, this covariance is a correlation. But it's a correlation because we fixed the factor variances both to 1. And so remember, the correlation is the standardized version of correlation, covariance, right? It's a covariance of variables with variances of 1. So 0.611 shows up right there. Does that tell you there are two distinct factors? I'd say yes.
Yeah.
They're distinct, they're just correlated.
Maybe, I'm not sure, I feel like
Where do you want your correlation to be?
yeah.
And I'm asking you this question, and I'm letting you argue it because this is the argument you're going to have with any reviewer you submit a paper to in the journal as well.
I'm thinking about higher order.
There's no higher order. You can't find in the higher order here because with two factors, it's unidentified.
Yes.
That's right. So this is two factors. No, that's good. I'm glad you asked that because this is something a reviewer would say too. Your questions are exactly the types of comments you would get in a paper if you submitted this. This is great. How would you answer that? What's a good correlation to have? I tell you this, like if the data, like what the data are telling you is the two-factor model fits way better than one. So you know it's not one thing. This factor, they're correlated at 0.611 in my practice, and I sound like a statistical yogi, right? Trying to do yoga with statistics. In my practice, I'd say this is a great correlation. This is they're distinguishable. They're going to be that you expect them to be related, but they're not so related where it's like 0.9, 0.95. The collinearity, by the way, I hate that. No, sorry. That's the first. And you're being a reviewer too. You make excellent reviewer 3s. I mean, if you want to go and go to YouTube and Google reviewer 3, and there's this internet meme again. Now we're talking about Nazis again. There's this movie about Hitler a long time ago, and it's him being mad at reviewer 3, with the subtitles. It's in German. Have you seen this movie? This internet meme where anyway. Honestly, I'm not into Nazis, I promise. But this is what the reviewers will say. Collinearity is a problem. Here's my philosophy on collinearity. It's a problem when your model blows up. Right? What happens, why collinearity becomes an issue, not only in SEM but also in regression, is you cannot take an inverse of a covariance matrix. Right? And that you cannot take an inverse of a covariance matrix if two variables are perfectly, if it literally is a linear combination present in your data. There's this potentially multivariate relation between the variables. When the model covariance matrix starts to go into where it can't get an inverse, on the computer there's certain things that get tripped. Basically values of features of the matrix, eigenvalues of the matrix start to become very, very small. And because of that, and what happens is you'll find standard errors that become super large. Like you'll see a parameter S of 0.611 with a standard error of 300,000, right? That's collinearity, and that's a problem. That's the only time it's a problem. That's it. That's it. So when reviewers have to say that in the reviewer Rolodex, I like to be like, here, math. Right? Other than that, it's fine. Yes.
So then in a paper,
Mhm.
so then what would you prefer to see reported?
Oh, the factor correlation, absolutely. In this case, and actually at the bottom of this, there's sort of an example write-up. I'd love to see the steps you took and why you took them. Right? And some of that has to be in an appendix if you don't have that much space, like where you would put your, or an electronic appendix where you put your files that you ran and your output or something like this. But basically, why did you choose to, what, in each step, why did you make the decisions that you made and what evidence did you use statistically to justify them?
If the correlation between factors are very high, it could be suggest that one factor.
That's right. That's right. So what happens is there's this. Each reviewer has their own tipping point as to where they complain about that correlation. Yeah. If you were a reviewer, you'd say 0.611 is too high. I've seen people be totally cool with 0.9 before, right? And so when you have that, one counter to if you said no, really, because these factors are correlated at 0.611, I don't believe it. I think there's one, not two. The counter to that would be to fit the one factor model. And we just did, and it didn't fit. Right? So we can say we have evidence to suggest the one factor model is inappropriate for this data.
But did we do the reverse coding?
Well, we could do that other model. Now that's an alternative model. I didn't try that here. And you could suggest that, and someone would think you rerun it or whatever else. That is an argument that's indistinguishable. That comes down to understanding what situational forgiveness is and whether or not there really is an N and a P version of it. I can't tell you that. That'd be something that you could try yourself. So this output looks, when you have two factors or 10 factors, it looks very familiar, right? You know where the factor loadings are, right? After each of the latent variables. You can tell whether they're significant, all of them are. You know, the covariance between the factors shows up here. You got your item intercepts, that's the same. Again, we did the z-score version of the identification, so our factors have zero means and they're not estimated, and you can see that because there's no standard error in each of those. Factor variances are 1. Those are not estimated. We see our R square. Now, one thing we can do is to tell whether or not our model 4 with 2 factors is fits significantly better than model 1 with 1 factor. Because, believe it or not, model 1 is nested within model 4. How is that the case? All right, well, if you take that covariance right here, and you allowed it to be 1, in this case, correlation, allowed the correlation to be 1, you've effectively made both factors the same. Right? So the way that you can get from a 2-factor model to a 1-factor model, when all the items only measure 1 factor, it's a little bit more complicated when you have cross-loading, but it still can be done, is effectively, imagine if you fixed this factor covariance to 1, factor correlation to 1, it would fit the same. And that's exactly what's happening here. If you look at this test, you can put, using the ANOVA model, the ANOVA function in R, you put both the models in because they're nested, it will not give you a warning. And it'll give you a warning about the scaling factor, that's just due to a simulation that's happening, I'm pretty sure. This is the chi-square test right here, the model difference. Actually, no, that is not the chi-square. It gives you the chi-square for each. It actually doesn't give you the p-value. I'm not sure why that is. Oh, I know why. Because the scaling factor is negative, it's not giving me p-values. And most, if you go look at the real data version of this, it's not negative. And in fact, for most of what you do, this is just fluctuation and randomness that's happening. But they give you a p-value, and that p-value would be non-significant. Pardon me, it would be significant. It'd be a very big difference between the two. In fact, if you wanted to try this, actually we could do it ourselves. Negative 11,343.483 is model 2. Negative 11,535 is model 1. So you can already see the difference is going to be about 400. Negative 2 times that difference is going to be about 400. Right? With 1 degree of freedom, which has a critical value of 0.3.84, right? So that's a huge number for 1 degree of freedom. I'm telling you that model 2 fits massively better, ridiculously better. I think that's a fairly safe word, right? Okay. So let's take a look at the model fit. So we saw model fit look good. Let's take a look at the modification indices for model 4. Take a look at the largest value. It is 1.280, which is way small. You see something like that, happy days are here again, right? Take a look at the normalized residuals. Here, the largest one is 0.382. Now remember, the scale of these things, they're like normal these z-scores, right? So the bigger they get away from 0, or the more positive they get, the more negative they get. The absolute value being big is huge. The biggest value, all right, there's a negative 6.44. That's also ridiculous fit. That's good, right? So here is our path model for it, path diagram. I hate that the color for the mean side dwarfs the color for everything else. There's probably better ways of doing it. Let me do this. Let me show you what happens for the real data, because the real data is a lot messier than the simulated. The way I simulated this, I probably could have done a better job. But let's go down to that same section for the real data. Oh, not that. Okay, so with the real data, it's not nearly as obvious that this is better. So what I did to simulate the data, I took model 4 and just generated data from it. I should have generated data from the saturated model, right, from where all the covariances were, because that'd be a little bit more accurate representation of it. So because I generated data from model 04, it's going to fit the best. Here's what happens in real data. Our chi-square value of 24.924 still significant. So yeah, I'm a little bit more unhappy about that. The RMSEA of 0.044, that's good. That's actually really good for RMSEA. You publish that, you publish this and have no problem. So I'm starting to be persuaded. Less than 0.05 for RMSEA.
And CERMA is 0.08, right?
0.08, right? But let's look at CFI and TLI, because that's my third destination here. 0.985 and 0.972. We want these to be above 0.95. Spot on that. Standardized root mean squared residual. This is the average correlation difference, essentially, is 0.029. That's good. So it looks good. The factor covariance, or factor correlation, is 0.564. Not overly high. Still messier, though, right? And if we do the model fit, the chi-square test of model fit difference, now we do get the value because we're not blowing up. It's significantly better than model 1. Now I want to make a note. For this test to be valid, you have to effectively say model 1 and model 4 both fit the data well, because model 1 didn't. Probably not all that valid, but it's this big of a number, people aren't going to complain about it. Put a caveat to it. So yeah, if we look at the modification index and we look at the scaled version of it, we'll see that there is an issue here with something about sit-n and situation 6. What's this operation tell us? Equal tilde, do you remember that? What that was? That was the latent variable definition. What this is saying is that the item 6 for the positive side wants to load onto the negative side too. But its value is 10.827. And the loading that you'd estimate for it would be 0.0245, which probably would be significant, but it wouldn't be very big. So there's a case to be made to say, it's there, but that could just be, it fits well enough as it is right now. We don't have to change it. Furthermore, if we look at the normalized residuals, you could probably pick where the big one's going to be, right? We saw up here, it was item 6 and sit n. So let's take a look at item 6. Sure enough, there's a big residual covariance, normalized residual right here, the biggest one we have in absolute values between situation 6 and situation 5R, and that's what's driving it to want to be on that. And actually, if you go up, this modification index right here would also take care of that same problem. Right? It's the residual covariance between situation 6 and situation 5R. So do you see a good sense for how to fix things a little bit now? Go back to the slides. I've got a couple minutes. That's notes. One couple of things I wanted to show you on the slides. Okay. One of the things that we talk about in slide, the error covariance that we just saw there, it said, hey, put an error covariance between situation 6 and situation 5R. Right? Which would be, if we were to draw it, it would look like something like this. It'd be this undirected path between these two variables, right? Which is basically saying that these two factors are not doing a good enough job describing the covariance between these two items, right? So it weakens your argument that those factors are really there, but it makes the model fit ridiculously better because that covariance, that normalized covariance in that spot, because we're adding a term to it, becomes 0. So every time we add a residual covariance, in the normalized covariance box that we see in our output, right over here, we take that thing right here and make it 0. So you can imagine it makes model fit better. It is like your quick band-aid for model fit. The problem with it is philosophically, what does that mean about situation N and situation P? It means they don't describe all the covariance that's going on in your data.
I think it's reasonable, although we have like we can the argument of our theoretical building of the model itself, but we would be much more better in like keeping away from undermining the assumptional validity.
I see there, and there is, and I will say there is sort of a there is sort of a way, there is an argument for it for that reason. That's why people do it. The question is, what type of paper are you using, right? If you're writing a paper saying, I've got this situational forgiveness scale and there's 2 factors, and then you go and undermine it with a residual covariance, it's not going to fly. If you're saying, I'm using these 2 factors to predict whether or not someone's going to, be involved in happiness or something like that, you're less concerned about the factors. Now you're looking for a predictor of something else, and yes, you'd probably want to put it there, right? So it makes sense. Like if the purpose of the paper sort of, there are journals out there that all they publish is results on scales, right? Journal of Assessments. One of them was Journal of It used to be Journal of Psychological Assessments. The APA journal, they publish a ton of volumes every year, issues every year, and everyone is a brief report about some new scale that someone has used either EFA or CFA or both on, and here right? So if that's the goal of what you're publishing, error covariance is going to weaken your argument. Right? If your other goal is, I'm looking for predictors that go and tell me what's going on with this behavior, and these are 2 circles that predict that, it's possible. But here's the problem with residual covariance, and this is a picture from Brown. The idea, having a residual covariance right here is indistinguishable from having another factor in the model itself. It's a covariance, that's right. Right? So you could have a case where you have, by the way, this model, it's a picture in his book, but it's unidentified. Playing tricks with data driving me nuts. But these, having this model right here and having this model right here, or this model right here, it's almost indistinguishable. So when you're adding these residual covariances, you're sort of, again, putting a Band-Aid on a problem, and sometimes you don't want that Band-Aid to be there, right?
So what about if the residual is like, what's the, I feel like, because if we want to measure like especially in the humanities and social sciences, it's very complex process to measure like latent traits.
That's right.
So believing that there might be other factors we are not aware of, maybe the covariance or the residuals, we need to mention it for like from an ethical and philosophical.
There may be a way. And again, there's no one size fits all for your argument.
But what I mean is that why not like putting like trying to put like a threshold for the residual, like to say it's tolerable.
You could do that too. You could say a small residual covariance is tolerable. Yeah, you could do that. I can see that. There's again, it's not a black or white type of issue. It's just I know from practice when if your goal is establishing validity that there's this two constructs underlying a scale, something counter that goal is adding an error covariance because you're saying there's something else out there aside from these two constructs that's underlying the scale. Right? So even just a matter of degree, right? You want it to fit well.
What I'm trying to, I'm connecting this to like the regression equation. We explained.
That's right.
Our model explaining this.
Right.
This is our error. This is what the scientific movement have been in this like after doing like many attempts to accomplish this. This is the. We need to work on this.
Right. Yeah, you could say that. Right. I mean, that's fine. That's exactly. And again, that's an argument you can make. And as a reader of papers, when you look at this, when you see the residual covariance, question should be why and what a person is saying about it. Right. One thing you should know, though, it is a way to make fit much better without having any description of why. Right? So now we got 1 minute left. So let me just talk about what's coming up next. So that is CFA from start to almost finish. What about the scores? What are we going to say about them? That's where we're going to come up next week. So next Tuesday we have class. We're going to talk about reliability. And now we're going to talk about reliability for what? What type of score? We'll look at a factor score. We're going to look at a sum score. And we're going to look at a combination of weird factor models that produce results of reliability that should be interesting for you. So what we're going to see is that the sum score matches the factor score when all the factor loadings are equal and all the residual variances are equal. When the factor covariance is set to 0. Who has that model? Does that work? When that model doesn't work, the sum score is not accurate. So all of a sudden you see people flip order when they should. So that becomes an issue. All right, I'm going to stop here. Once again, next week we have Meet Tuesday, but next Thursday I'm out. I'm giving a lecture in Colorado on Friday. I won an award. My award to go give a 90-minute lecture. So yeah, thank you. But no, but we'll have class once next week. If you have questions at homework, hit up Lou. I'm going to be gone this weekend, but hit up Lou. And if you can't get for whatever reason it doesn't work, both of you can email me and we can make this work. Okay. Thank you.